Good morning everyone. Now I'll start here the linear differential equations. A differential equation is said to be a linear differential equation if it contains the dependent variable and its differential only with first degree, and it doesn't contain any products like product of the dependent variable with the derivative or product of the derivatives. Then such a differential equation is called linear differential equation. I'll repeat that once again. A differential equation is said to be a linear differential equation if it contains the dependent variable y and its differential with only degree 1, and it doesn't contain any products like product of the dependent variable and its derivative or product of the derivatives. Otherwise, we call it as a non-linear differential equation. The standard form of linear differential equation. Before going to that standard form of linear differential equation, we see few examples of linear differential equation. Example: x into d square y by dx square plus 2 into dy by dx plus y equal to e power x is a linear differential equation. If you observe this has derivatives with only power as 1, means degree as 1, and it doesn't contain any product terms. Therefore, this is called a linear differential equation. If we take another example, y into d square y by dx square plus 2 into dy by dx plus y equal to cos x is a non-linear differential equation. Why we are calling it as a non-linear differential equation? If you observe the first term, it has y into d square y by dx square, derivative of y with respect to x into the dependent variable. As it is containing the product y into d square y by dx square, such a differential equation is called as non-linear differential equation. Am I clear? Then the standard form of linear differential equation. A linear differential equation of the form dy by dx plus p of x into y equal to q of x is called a linear differential equation in y, where p and q are the functions of x. Yes. If you see this example, y into d square y by dx square plus 2 into dy by dx plus y is equal to cos x, it is clearly a non-linear differential equation as it contains a product of the dependent variable and its derivative, that is y into d square y by dx square. So such a differential equation is a non-linear differential equation. We write about the standard form of the linear differential equation in y and the standard form of linear differential equation in x. A differential equation of the form dy by dx plus p of x into y equal to q of x is called linear differential equation in y, where p and q are functions of x. P and q are functions of x. So this particular differential equation dy by dx plus p of x into y equal to q of x is called linear differential equation in y. So how to write its solution? We'll learn next. To get the solution, to get the general solution of linear differential equation, multiply both sides by e power integral p dx. Then we get dy by dx into e power integral p dx plus p y into e power p dx integral p dx equal to q of x into e power integral p dx. We are multiplying both sides by e power integral p dx. If you observe this, we can write it as d by dx of y into e power integral p dx, which is equal to q of x into e power integral p dx. If I differentiate this one, as this has two terms, it follows UV rule. So if I differentiate this by using the UV rule, I'll get back this one. So that's the reason I'm clubbing these two terms and I'm writing it as d by dx of y into e power integral p dx, which is equal to q of x into e power integral p dx. Integrating with respect to x, we get y into e power integral p dx is equal to q of x integration q of x into e power integral p dx into dx plus some integrating constant c, or I can write it as y into integrating factor equal to integration of q of x into integrating factor dx plus c. This is the general solution of linear differential equation in y. Similarly, we can write the linear differential equation in x. Linear differential equation in x. It is given by dx by dy plus px equal to q, where p and q are the functions of y, where p and q are the functions of y. Similarly, we can get the general solution of this particular case. Its general solution is given by x into integrating factor equal to q into integrating factor dy plus c. Here, integrating factor is equal to e power integral p dy. If you observe there, the previous one, the integrating factor was e power integral p dx. In this case, as x is depending on y, the integrating factor will be e power integral p dy. Now we'll see few problems based on this linear differential equation. Problem 1. Solve x plus 1 into dy by dx minus y equal to e power 3x into x plus 1 whole square. Solving x plus 1 into dy by dx minus y equal to e power 3x into x plus 1 whole square. If you observe, this is not directly in the form of linear differential equation. So we have to divide it with the term x plus 1 to make it a linear differential equation. Given differential equation is x plus 1 into dy by dx minus y equal to e power 3x into x plus 1 whole square. To make it a linear differential equation in y, divide by x plus 1. So that gives dy by dx minus y into 1 by x plus 1 equal to e power 3x into x plus 1 whole square by x plus 1. Yes, we divided the complete equation with x plus 1 to make it a linear differential equation in y. Now if you observe, this is of the form dy by dx plus py equal to q, where p is equal to minus 1 by x plus 1 and q is equal to e power 3x into x plus 1. After this cancellation, we get q of x as e power 3x into x plus 1. Then we have to find the integrating factor. Integrating factor is equal to e power integral p dx. So that is equal to e power integral minus 1 by x plus 1 into dx. So which is equal to e power minus integration of 1 by x plus 1 dx. We know that integration of 1 by x is log x. In the same way, integration of 1 by x plus 1 is log of x plus 1. So that becomes e power minus log of x plus 1. That is, k log x is equal to log x power k. So we can write this as e power log of x plus 1 whole power minus 1. And we also know that e power log m base e is m. So therefore, this becomes x plus 1 whole power minus 1. And we can write this as 1 by x plus 1. So therefore, the integrating factor for this given differential equation is 1 by x plus 1. So therefore, general solution is given by y into integrating factor equal to integration of q into integrating factor dx plus c. Y into integrating factor. So y into 1 by x plus 1 is equal to integration of q. Q is e power 3x into x plus 1, and integrating factor what we got is 1 by x plus 1 into dx plus c. So this x plus 1 and this x plus 1 will get cancelled. So we get as y into 1 by x plus 1 equal to integration of e power 3x. We know that integration of e power ax is e power ax by a. So we get here that as e power 3x by 3 plus some constant c. This is the solution of the given linear differential equation. Solve 1 plus y square into dx is equal to tan inverse y minus x into dy. Here, this is again not given in the proper order, so we have to rearrange the terms so that we can get linear differential equation in y or the linear differential equation in x. Or divide this given differential equation by 1 plus y square. 1 plus y square. Can I make it a linear differential equation or not? So if I divide this by 1 plus y square, then I get that as dx is equal to tan inverse y minus x divided by 1 plus y square into dy. Then rearranging the terms, I get that as dx by dy is equal to tan inverse y by 1 plus y square minus x by 1 plus y square. Then we know that the linear differential equation in x is of the form dx by dy plus px is equal to q, where p and q are the functions of y. So we have to arrange this differential equation in the same way. So dx by dy plus x into 1 by 1 plus y square is equal to tan inverse y by 1 plus y square. If you observe, it is following the same pattern. Dx by dy plus px is equal to q, where p and q are the functions of y. So it is a linear differential equation in x. Where p is equal to 1 by 1 plus y square and q is tan inverse y by 1 plus y square. So to find the general solution, first we need the integrating factor, and it is given by integrating factor is equal to e power integral p dy. As x is depending on y, the integrating factor will be in terms of integrating with respect to y. So e power integral p dy, which is equal to e power integration of 1 by 1 plus y square dy. And we know that integration of 1 by 1 plus x square dx is nothing but tan inverse x. So therefore, I get this as e power tan inverse y as the integrating factor. Its general solution is given by x into integrating factor equal to integration of q into integrating factor dy plus c. So it implies x into integrating factor, I got that as e power tan inverse y, which is equal to q. Q we got that as tan inverse y by 1 plus y square, and the integrating factor is e power tan inverse y into dy plus some constant c. Now for solving this, I can take the substitution as tan inverse y is equal to some p. Then differentiate with respect to y, or differentiate simply. So we get that as tan inverse y is equal to p. So I'll get that as 1 by 1 plus y square dy is equal to dp. 1 by 1 plus y square dy is equal to dp. Now replacing this in the above differential equation, I get that as x into e power tan inverse y equal to tan inverse y, I made that as p. So I'll write it as p into e power p into, and if you observe from this, dy by 1 plus y square has become dp. So therefore I'll write it as dp plus c. Now we have two terms like u and v, integration of uv. Either we can use integration by parts or we can use Leonard's rule of integration. We know that integration of uv dx, Leonard's rule, is u v1 minus u dash v2 plus u double dash v3 minus and so on. This is an alternating series, u v1 minus u dash v2 plus u double dash v3 and so on. Here this subscript 1 represents one-time integration and the superscript, that dash, represents one-time differentiation and so on. So here I'll take this as u and this as v, as I should take u as that term which can end after some time. So if I take p, its differentiation will be 1. If I differentiate 1, that will become 0. So in such a way, I'll select u. So this gives x into e power tan inverse y is equal to u v1. So p into integration of e power p. We know that integration of e power x is again e power x. So I'll get that as e power p minus u dash, means differentiation of p once. So that will give me 1. And v2 is nothing but integration of e power p twice. We know that integration of exponential function any number of times will be the same. So therefore, I'll get back again the original function e power p plus some constant c. Then the general solution is x into e power tan inverse y is equal to p. P, we have taken the substitution p as tan inverse y. So I'll replace it back. So I'll get that as tan inverse y into e power tan inverse y minus e power tan inverse y plus some constant c is the solution of the given linear differential equation in x. Similarly, we have to solve the problems based on linear differential equation in y and linear differential equation in x.